Have you ever thought of a desert as synonymous with scorching heat and endless sand dunes? Well, Antarctica defies all those expectations. Yes, we're talking about the largest desert on the planet. Surprising, isn't it? Less than 250 millimeters of precipitation falls there over the course of a year, meaning this vast frozen expanse receives less water than the Sahara. In some regions, there hasn't been a drop of rain for at least 2 million years. Antarctica isn't just the largest desert, but also the place where the lowest temperature on Earth was recorded, -89.2 degrees Celsius. Cold enough to freeze the air around you. Cold enough to make the heat of a freezer feel like relief. It's the kind of cold where even movement becomes difficult, and exposed skin for just a few seconds can suffer burns, known as frostnip. If you think the cold in Antarctica is extreme, wait until you discover what the climate is like on Mars. On Martian soil, winter nights can bring a soul-freezing chill, reaching -125 degrees Celsius. But that's just the beginning. Traveling even further, we arrive at Neptune, the coldest planet in the solar system. A gas giant with an atmosphere composed of hydrogen, helium, and methane gases that contribute to the temperatures plummeting to an astonishing -220 degrees Celsius, an eternal winter. In this environment, the air itself becomes liquid, and survival becomes a distant thought. But why is space so cold? Space is extremely cold because it is an almost complete vacuum, with few particles to transfer heat. Without air or matter to conduct or convect heat, transfer occurs only through radiation, which is less efficient. Additionally, the vast distance from stars, which are the primary sources of heat, means the distant regions receive little radiation. But if we leave the solar system and travel 5,000 light-years to the Boomerang Nebula, also known as the Bose-Einstein Nebula due to its shape, we'll discover the coldest place ever recorded and known to mankind. In 1995, a team of astronomers used a spectrometer to analyze the light emitted by the nebula at different wavelengths and found it was at a temperature just 1 degree above absolute zero, meaning it was recorded at -272.15 degrees Celsius. It's believed that the low temperature of this point in space is due to the rapid expansion of gas expelled after the death of the star that gave rise to this nebula, causing an adiabatic cooling effect. But even though this is the coldest spot ever found, it still doesn't reach the absolute minimum. The point where cold reaches its peak and the very notion of movement ceases to exist. This point is absolute zero, which equals -273.15 degrees Celsius or -459.67 degrees Fahrenheit. It is the temperature at which matter reaches complete immobility. Below that, nothing can exist, because nothing can move. The particles that make up everything around us simply freeze. Absolute zero is an unbreakable limit, a point where the universe seems to come to a standstill. When we talk about extreme temperatures, we need a scale that goes beyond our everyday experience. That's where the Kelvin scale comes in, the tool scientists use to measure cosmic cold. Unlike the Celsius and Fahrenheit scales we're familiar with, the Kelvin scale starts at absolute zero, the point where particle motion simply ceases. In science, talking in Kelvin is crucial for studying not only space phenomena but also experiments in laboratories here on Earth, where we recreate conditions so extreme that the concept of Celsius or Fahrenheit no longer makes sense. Temperature, at its core, is movement. The hotter something is, the more the particles that make it up move. For example, in a hot cup of coffee, the heat you feel is the result of those particles vibrating intensely, whereas in a frozen lake during winter, the particles move much more slowly, almost coming to a halt, but there is still some movement. At absolute zero, all that movement completely ceases. However, even though absolute zero is the theoretical limit of temperature, there's a fundamental obstacle that prevents its full realization: Heisenberg's uncertainty principle. This principle states that it's impossible to know both the exact position and velocity of a particle with total precision at the same time. This means that even at extremely low temperatures, particles still retain a slight oscillation. They can never be completely still. Even in the coldest places in the universe, like the Boomerang Nebula. When scientists achieve incredibly low temperatures, something truly strange happens to matter. The atoms, which usually move independently, begin to behave as if they were a single superatom. This was a phenomenon first theorized by Albert Einstein and Satyendra Nath Bose, and it was only proven in the lab in 1995, becoming known as Bose-Einstein condensate behavior, a phase of matter formed by bosons at temperatures very close to absolute zero. Under these conditions, a large fraction of atoms reaches the lowest quantum state, and quantum effects can be observed on a macroscopic scale. It's as if several distinct particles merge into one, losing their individual identity. This state of matter opens doors to revolutionary research, such as simulations of black holes and new ways to explore the laws of physics, altering our understanding of how matter can behave under extreme temperatures. Another example is when helium is cooled to extremely low temperatures, around 2 Kelvin or minus 271.15 degrees Celsius, it enters a completely new state of matter, the superfluid liquid that loses all viscosity or friction. Remarkably, it can climb up the walls of a container or even pass through solid barriers. Amazingly, the coldest place in the universe isn't lost in some distant galaxy or nebula but was created right here on Earth. In 2021, a team of physicists achieved the lowest temperature ever recorded, reaching 38 picokelvin, or 38 trillionths of a degree above absolute zero. While thermodynamics prevents us from reaching absolute zero, basic research has allowed us to get extremely close. To do this, researchers started with a cloud of 100,000 rubidium atoms trapped in a magnetic field inside a vacuum chamber. They then cooled it to form a Bose-Einstein condensate. Initially, they managed to reach 2 billionths of a degree above absolute zero, but that wasn't enough. That's when the simulation of a space vacuum environment came into play. The scientists took the experiment to the European Space Agency's Bremen Drop Tower, a microgravity research center at the University of Bremen in Germany. From a height of 120 meters, the team dropped the apparatus containing the Bose-Einstein condensate, and during the free fall, the magnetic field trapping the gas was quickly turned on and off. This allowed the condensate to float in the absence of gravity, reducing the molecular motion of the rubidium atoms. The result, a temperature of 38 picokelvins, sustained for about 2 seconds, colder than any other natural point in the known universe, including the Boomerang Nebula. By approaching these extremely low temperatures, scientists can observe remarkable quantum phenomena such as superfluidity, superconductivity, and ultracold atomic condensation. But tell me, did you feel a chill after watching this video? If you enjoyed this journey to the limits of cold in the universe, make sure to subscribe to the channel so you don't miss any details of our upcoming discoveries. I'll see you in the next video.